Welcome back to ECE 441, 541, or 501B. Sorry, I'm a few hours late for that operation or that class, but this is 501B. Homework number 3 is due on Friday, and your first exam is a week from Wednesday. Is that correct? I think those are the right dates. What I want to do today is pick up where we stopped last time. Last time we actually had a weather event. If you remember, we didn't meet last time, but we were told to maybe not have, well, we were encouraged to maybe not have class. So I had meetings through class and went home and tried to record the lecture. Hopefully you've seen that. We're picking up where that left off. So there was a lecture on that day a week ago, well, not quite a week ago, but on a Wednesday of last week. And we were talking about how do you represent matrices for a linear map. And we're going to do that today using different basis representations for the vectors. And we'll go from one location to another location with a linear map, and it will find the matrix that takes us from point P to point Q under two different bases. And we'll see, or we'll learn that that map is not this, that matrix is not the same. The map is the same, but the matrix representation of that map looks completely different. I guess what I was going to start today's class with was when is T1 and show you what T1 looks like, equivalent to T2, and they're not equal, but they're equivalent. And that's what we'll see in this first part of today's class. Then we will quickly breeze through what you can do with matrices, and I'm assuming we all know how to add matrices, how to multiply matrices, how to multiply a matrix with a vector. Maybe we will get further along, but if we don't, it may be on you to finish up chapter 3, which is going to be talking about invertible maps. We have maps between two vector spaces. We know what it means to be injective, or one-to-one, or to have a trivial null space. We know what it means to be surjective, to be onto, to cover the entire codomain with our linear map that's mapping from the domain into the codomain. If we have both, if we have a map that's both injective and surjective, then it is an invertible map. And that's an if and only if relationship. Once we have an invertible map, we can now talk about when are two vector spaces equivalent. And that's when they would, or when are they isomorphic, or when are they similar. So maybe the better word, I shouldn't have said equivalent. Isomorphic. That means these are similar vector spaces and they're related by an invertible map. You can basically map from one to the other and they are isomorphic to each other. Then you can actually restrict your codomain to be the same vector space as your domain, and then it's called an operator. When your linear map goes from a vector space back into the same vector space, that then is called an operator, which is a specialization of a linear map. And that is sort of the last piece of chapter 3. Let's start by looking at an example where we are actually going to have a matrix representation of this linear map T, and let's just play in a space that we can sort of sketch. Let's go ahead and not be a dimension reducing map. Let's just go from the plane into another plane. V then is R2, and W also is R2. And what we want to do is examine a point, P1. So think of a point on the floor, and you now want to map that point to another point on the floor, and you want to see what that mapping looks like in terms of a matrix representation if you use different basis vectors to represent the point and a different basis to represent the endpoint, the starting point and the endpoint. We want to look at what that map looks like, and before we even get into the mapping, let's look at the point P1 using different bases for the representation of P1. Let me see if I can make it clear what I mean by that. Suppose that we now have our plane, that's R2, and let's have two different bases in that plane. Let's let one of those, let me go ahead and say there's one and there's one, a distance of 1. Suppose that we now say that V1 is that vector and V2 is that vector. Those are our standard basis, V1 and V2. The other basis that we will use is, let's say we just rotate those bases counterclockwise by 45 degrees, and let's actually allow them to expand so that, let's call this one V1 bar, and that basis vector V sub 2 bar. That's just a rotated by 45 degrees counterclockwise and grown a little bit by this scaling factor, let's say the square root of 2, in length. And we haven't even talked about length, but it's a little bit longer. And let's go ahead and say that our starting point is the point P1. And how we represent P1 depends on which of these sets of basis vectors we use. So the basis vectors actually change how P1 is represented in a vector notation or by a vector. That's maybe a little bit wordy, but hopefully it will make sense. Let's say that we now are defining two different bases. Let's say V, capital V, is made up of V1 and V2. Columns V1 and V2. And let's let V bar be the other representation, and let's call that V1 bar and V2 bar. This is now our standard basis for V. And this set of basis vectors is rotated, CCW, or counterclockwise, and stretched a little bit. So now let's represent, is it clear what V1 and V2 and V1 bar and V2 bar are? V sub, yes. Pardon? So these are, so the question is, are we dealing about span? Actually, I'm trying to just say that we are going to use these vectors to represent any point in R2. So we are going to parameterize a point in R2 in terms of V sub 1 and V sub 2. Or we are going to use the barred basis and represent that point in terms of v sub 1 bar and v sub 2 bar. Okay, and they do span all of R2, these two vectors. That's why, what do we know about a basis set? Yes, so they have to be linearly independent and they have to span the space. And those two actually do that, those two sets of vectors. Is that okay? So the capital V is just a notation that I'm going to say is that's the matrix little v1 and little v2. So I guess in the past I'm overusing V, capital V is overloaded. So here capital V, maybe I should, well, I don't want to give it a subscript, but capital V does not, it does mean the generic domain, but in this case I'm saying this capital V is going to be the matrix composed of those two basis vectors, little v1 and little v2. Okay, now I maybe understand a little bit more where the confusion might be coming from. But hopefully it's clear from the context. That was what I was hoping. So let's now say that we are representing the point P1 in terms of the V basis vectors. So the vectors in that matrix, capital V. And we'll have another representation where we may have the V bar basis vectors. Hopefully that's clear. But now what I'm wanting to say is that I now have V times A1, A2, and I want to know what do A1 and A2 equal in a vector. This is now V1 concatenated with V sub 2, little v sub 1 concatenated with little v sub 2. And that then is going to be scaling A1. So I'm using matrix vector multiplication before we even talk about it. So maybe that's a poor choice. I'm overusing some of this, but this is now A1 times V1 plus A sub 2 V2, or A1 1 0 plus A sub 2 0 1. That's another way of thinking about what we're doing for we're trying to find A sub 1 and A sub 2 to produce our point P1 in the two-dimensional plane. We want to find what A sub 1 and A sub 2 are equal to. And that now, if we go back to what P1 is, that's supposed to be at a location in our standard basis, one unit in the horizontal direction and one unit in the vertical direction. Little v sub 1 just goes in the horizontal. Little v sub 2 just goes in the vertical. And what I'm trying to say is that now A1 is equal to 1 and A sub 2 is equal to 1 in this basis that we've selected, that I'm calling little v1, little v2. Those are our basis vectors. Or I might now say that that's P1 in the capital V basis we can represent as 1, 1. So we take the top coordinate, and that's going to scale the first basis vector, and we add that to the second coordinate of P sub 1 capital V, and that's going to scale the second basis vector. That's a linear combination. So A sub 1 is 1, A sub 2 is 1. Let's see what P1 is in terms of V1 bar, V2 bar, and I think it's clear from the picture what that better be. It better just be V sub 1 bar. That puts us to the same location of P, or P1. Is that clear? So if we do the same analysis with the barred basis vectors, we better just have V1 bar and no v sub 2 bar. And that will get us right to that point P1. So now if we say, let's talk about representing P1 in terms of the V bar basis vectors. If we do the same process, we have the two vectors concatenated in a matrix that I'm denoting as capital V bar. That now, let me just change my notation to mean that now I'm using some new coefficients, A1 bar and A2 bar. That's now 1, 1. That was, I hope, what we called V1 bar. And V2 bar was minus 1, 1. Minus 1 in the horizontal, 1 in the vertical. That's how we can represent V sub 2 bar. Those are my basis vectors combined into one matrix. Yes? Yes, so now we have, so the question was, we're still expressing these with respect to the standard basis. We have to have some way of keeping track of things, and it's just intuitive that we usually have first coordinate maybe in the horizontal, second coordinate in the vertical. But yes, we have to somehow have a notation for how do we represent these vectors. And so the first coordinate in these vectors corresponds to the horizontal direction. The second coordinate corresponds to the vertical direction in my diagram, in R2. These two columns, then, we want to find how do we combine those by the choice of the scalars A1 bar and A2 bar to produce the point P1 in this new basis V bar. Meaning we now have A1 bar times 1, 1 plus A sub 2 bar times minus 1, 1. This is now V1 bar, V2 bar. And as I said, we now need to produce this location, one horizontal, one vertical. That can be done by setting A1 bar equal to 1 and A2 bar equal to 0, which now says that P1 in the V bar basis is 1, 0. Meaning, I could say the point P1 is at 1, 1 in the first basis, or it's at 1, 0 in the second basis. And I need to tell you, if I tell you P1's at 1, 0, you need to say, what are my basis vectors? Then I would have to tell you, oh, the first basis vector is 1, 1, and the other basis vector is minus 1, 1. And now you know that you're combining one of the first basis vectors and none of the second basis vectors to produce P sub 1 V bar. Yes? We are still dealing with the plane. We're still dealing with the plane, and I've now painted a point on the floor, and I'm calling that point P1. How we actually define that point depends on how I lay out my coordinate system or my basis vectors. Okay, so in one way I said I want to go one horizontal, one vertical. Those are my basis vectors. In the other case I said I want to go actually square root of 2 at 45 degrees. That's my first basis vector. And then I want to go square root of 2 at 135 degrees, that's my second basis vector. And I want to represent that point on the floor in the first basis set and the second set of basis vectors. And depending on which set of basis vectors I use, and you could have many different representations, vector representations for that same point P1, because we could all have a different set of basis vectors as long as they are linearly independent and span the space. Yes? Is our matrix A a linear map? So I don't have yet a matrix. All I have is a vector. I have basically weightings of my basis vectors. For P sub 1 V, capital V, I'm just saying these two coordinates, the top one and the bottom one, let me call them top and bottom, are 1 and 1. The top one weights V1, the bottom one weights V sub 2. If I want to go horizontally, I need to go scale it by the top coordinate. If I want to go vertically, I need to scale it by the bottom coordinate in this basis. If I change my basis, then I may have to move different, or I may have to select different weightings of my basis vectors to get to the same point or to the same location. Let's now, so that's just sort of what does a vector look like, or what do my weights of basis vectors look like if I have two different basis sets or two sets of basis vectors. Let me throw you another level of complexity. Now let's introduce a linear map. And suppose it's a little bit challenging, I think, to figure out what kind of notation to use. So I'm going to call X my first coordinate and Y my second coordinate in the domain. And I'm going to have that mapped into, let me just say, the top coordinate will be, I'll take 2 times the top minus 1/2 the bottom for my first coordinate. And the second coordinate, let me take the top and add to that twice the bottom. i.e., or that is, T is a linear map from R2 back into R2. But to make it even more confusing, let me introduce two bases for the codomain. So this, let's say is, oh boy, this is really overloading now. Here's V and here's W. Maybe I should have said something about, I don't know. How do I do that? Maybe I should have done this as a script V or something. Capital script V. So now I'm really overloading, but V and W, that's my domain and codomain, not my basis vectors, but I'm sort of using the same so that you know what I'm talking about, but maybe it's making it more confusing. Here, I'll confuse you even more. Let's let one of the sets of basis vectors be W. What do you think that's going to be? Let's just make that be our standard basis. So this is now a matrix. If that's confusing you, forget that for now. Okay? Just say domain and codomain. With W, I'm going to call this W1 and this W2, and that's the standard basis again. And let's let W bar, a different set of basis vectors, be 1, -1, and 1, 1. And I'll call this W1 bar, W2 bar. Pictorially, what that is that's now a rotation clockwise. We now are down here and here. If this is 1 and 1, there's W1 bar, and this is now W2 bar, where this is our standard basis, and W bar is a rotated, but now it's rotated clockwise, and stretched. Pardon? Yes, so these basis vectors are in the codomain. This is how we are representing our vectors in the codomain, either with the standard basis or a rotated clockwise and stretched set of basis vectors. Okay? So now what we want to do is see what T looks like using different basis vectors from this set of basis vectors that I've tried to represent. Here's the question, or the idea that we're trying to understand. What does this linear map T look like as a matrix for, let's say, the first case A, where we are going from the domain to the codomain with T, and the basis vector here, let's let that be the set denoted by the matrix capital V, and our codomain, let's let that be W. Versus, and compare that with B, where our domain now and codomain have different basis vectors. Let's let the domain in the bottom be V bar, and the codomain have a basis W bar, and have the same linear map applied to it. And we want to know what's the matrix for case A and what's the matrix for case B. And they better take us from the same point, P1, to the another same point, Q1, based on that linear map that we defined. That was defined by T, that essentially says grow in the X direction and contract and change, go opposite in the vertical direction for the first coordinate, and then just go in the same amount in the first coordinate and stretch in the vertical direction for the second coordinate. Now, how do we do that? And this is where I think we sort of left off last time. We were talking about linear maps in our rain delayed lecture. So that's what we'll say. We had a rain delay because I don't think it was done at 4 o'clock on Wednesday. I think it was a 4-hour rain delay. I think it was about 8 o'clock when I started doing that lecture. But I'm sure you're looking at what time it is in the lower right-hand screen on YouTube and going, wonder when he did this lecture. He sounds like he's half asleep. All right, so let's look at case A. Case A. We have V, which is 1, 0, 0, 1, and W, which is also 1, 0, 0, 1. Those are actually the standard basis. And that's, if we don't say otherwise, that's usually what we're using, and that's how we think, vertical and horizontal, or I'm sorry, horizontal and vertical in an R2. And in this case, we have the span of V equaling R2 and the span of W equaling R2. And we could say that that's the span of these two vectors, 1, 0, 0, 1, if we wanted to. Or that's now the span down here, the same vectors. And we want to now use that underlying basis in the domain and the codomain to figure out what the matrix looks like, to take us from a point. What happened? Pardon? 1, 0, 0, 1. Is that okay? So that should be the same. I'm using the same basis in the domain and the codomain. So I haven't changed my underlying set of basis vectors. That's what I'm trying to say for this example. So now, if you're thinking about it, the way we normally process horizontal and vertical, that's what we're talking about in terms of representation. We want to now find out what's the matrix representation, a matrix that will produce the linear map that we introduced, where the linear map is T equaling 2x minus 1/2 y and x plus 2y. And the way that we do that is we now look at how that linear map, what it looks like for each of the basis vectors in the domain in terms of what it looks, or what that looks like in the codomain's basis. Can that be any more confusing? So let's look at TV1, which is T operating on 0, 1. And what does that produce? Using this way of mapping, we're just setting x equal to 1 and y equal to 0. That should produce a vector of 2, 1. Is that okay? But now what we want to do is we want this location, or this vector, to be described in terms of the basis vectors in the codomain. And in this case, they're the same vectors, so it's going to look trivial, but let's go through that process. We want that now to equal, we want to be some linear combination. Now I'm really getting crazy with my notation, but now I'm going to double subscript these a's. I want this to be the first vector in my codomain's basis set, and this is associated with the first vector in my domain. That's what the A11 represents. That will now be times 1, 0 plus A. This is now going to be processing or weighting the second basis vector in my codomain to yield the basis vector being operated on by the linear map in my domain. And that is 0, 1. Can I make that any? Well, let me label that in just a minute. So what do A11 and A21 equal? Another way of viewing this is we now actually could say, well, that's W1 W2, where this is W1 and this is W2, we could get the same result by doing that, where W1 is this column 1, 0, and W sub 2 is a column 0, 1. Or we could say W of A11, A21. But that's just 1, 0, 0, 1. And that was supposed to equal, from up above, 2, 1. And since that's the identity matrix, that actually tells us what A11 and A21 are equal to. We now know that A11 and A21 are equal to 2, 1, where this first subscript corresponds to the first basis vector in W. This corresponds to what? That's the second basis in W. So now I'm indexing, on the first index is my codomains indices. This is the second basis in W, or corresponds to that. And this last coefficient, or the second coefficient in both, are associated with the first basis vector in the domain, which we represented as V. And that column 2, 1 is actually going to be the first column in our linear matrix representation, in the map, in our matrix representation of this linear map. That's the first column in our matrix, meaning all we've done is we've now figured out how to write the linear map operating on the first basis vector in our domain in terms of the basis vectors in the codomain. We now need to figure out what's the linear map doing to the second basis and write that now in terms of our codomain's basis vectors. If we do the same thing for the second vector, we now have T applied to V sub 2, or T is now going to operate on 0, 1, and if we remember what our linear map was telling us, at 0, 1 we replace all the x's with 0 and the y's with 1, and we're going to end up then at minus 1/2, 2. And that's supposed to equal some linear combination of the first basis vector in our codomain plus some scalar multiple of our second vector in the codomain's basis. And that's, I hope, consistent with our notation. The second subscript corresponds to the second vector in our domain's basis getting mapped through the linear map, and the first subscript corresponds to the basis vector in our codomain that it's weighting. Or this now says that we have W1, W2, and that creates a matrix times A12, A22. That's 1, 0, 0, 1 times A12, A22, or that now says that A12, A22, because it was trivial to solve that system of equations, that's equal to minus 1/2, 2 That's now our second column in our matrix representation. And we will now say that the matrix of the linear map T that maps from some set of basis vectors, and maybe the book uses the following. Maybe I was getting lazy. Some set of vectors, which we called capital V, but we could just isolate those or represent those as little v1, little v2 into little w1, little w2. That's now in terms of those two basis vectors sets. It's our first vector, which is 2, 1, makes up the first column. The second column is minus 1/2, 2. And we can now use that, if we wanted to produce Q1. Meaning, if we now said Q1 in W equals what? So that's now this matrix, and I don't know what notation I'm going to use for that. I could just call this A. It's a matrix. This is now A times P1 in V, which says that we have 2 minus 1/2 in the top row, 1, 2. And what was P1 in our original basis? It was just 1, 1, wasn't it? Wow, that was a ways up there. 1, 1. So that Q1W as a point, this tells us we started at the point 1, 1, and we're going to move to a new point based on a linear map that we now have a matrix representation for, and that new point we're calling Q1 in the basis W is going to be 2 minus 1/2, which is 3/2. And again, that means 3/2 in which direction? Horizontally, because that's how we've defined this basis set in our codomain. And then it's going to be 1 plus 2, or 3, in the vertical. And these are how we normally think about those coordinates, horizontal and vertical. So we've gone from 1, 1 to a little bit more in the x direction and quite a bit more in the y direction to get to Q1 from that linear map, which we now represented by a matrix A. Let's look at case B. So we're looking for an A in the other case, but we'll call it something else, maybe an A bar. Yes? Yes, so the way that we think about this particular linear map in the normal standard basis, you could find out what Q was by plugging in x equal to 1 and y equal to 1 in this representation and get the same location or point, which should be 3/2 and 3, which it is. But I don't really want to do that because now we're talking about representations in matrices. Let's look at case B. What was case B? We want to now find what is the matrix representation of this linear map T. It's the same linear map. We want to go from P1 to Q1, but now we know P1 in this basis is 1, 0. And we want to take that through a linear map or through a matrix to find Q1. And we want to end up in the same location, where here we are going to say V1 bar, V2 bar, W1 bar, W2 bar. We want to find that, and maybe we'll call that eventually A bar, since that's the barred place. And A is not going to be A bar, but they will give us equivalent maps. They should. So how do we find the first column in A bar? What's our strategy, or what's the process? We now want to find out what happens when we apply that linear map to the first basis vector in our domain, T operating on V1 bar. What was V1 bar? This was where we rotated, which way? Counterclockwise. So now we rotated counterclockwise. This was now 1, 1, wasn't it? That was V1 bar. Pardon? Yes, so now we're taking a new basis in our domain, which we called the capital V bar basis, and we're going to use that basis to represent the point that we're starting at, and we're also going to say we need to find the linear map, or I'm sorry, the matrix that corresponds to this same linear map when we take any point in that new basis, the V bar, into a vector represented by the W bar basis. We want to find the matrix that provides that map. In this case, what is this? Well, this is now 2 times the first coordinate minus 1/2 times the second, and x plus 2 times the second. Or 3/2 and 3. And we want to find that, or that better equal now, the first basis. We need to scale the first basis in our codomain, which our codomain's first basis was 1 minus 1. Is that right? And this is now the first basis vector of our domain plus a sub 2, 1. And this was, I think, 1, 1. Meaning this is now A1, 1, W1. Let me bar these. So those are barred. This is barred and that's barred. Plus A2, 1 bar, W2 bar. Or, you can see we can write this many different ways. There is W1 bar, W2 bar, scaling A1, 1 bar, and A2, 1 bar, scale those two vectors or those two columns. So this is now 1 minus 1, 1, 1 times A1, 1 bar, A2, 1 bar, and that's supposed to equal 3/2 and 3. But we have, although we haven't talked about it yet, I think you know how to multiply matrices. This now produces A1, 1 bar plus A2, 1 bar and minus A1, 1 bar plus A2, 1 bar. Is now equal to 3/2 and 3. And we need to find these A's, barred, that weight the codomain's basis vectors in this W barred basis set. And we can do this many different ways. We could have inverted that 2 by 2 matrix and found A1, 1 bar and A2, 1 bar. Let's just treat it as 2 equations and 2 unknowns just to do something differently. This is now 2 equations and 2 unknowns, meaning we now have an A1, 1 bar plus an A2, 1 bar equaling 3/2. and a minus A11 bar plus an A21 bar equaling 3. If we add those together, we have 2 A21 bar is equal to 3 is 6 halves, so we have now 9 halves for that, or A21 bar is a little bit more than 2. It's 2 1/4, or 9/4. And we can now use either one of those original equations and replace A21 bar with what we know it equals to find or solve for A11 bar. A11 bar is now 3 halves minus 9/4, or 6/4 minus 9/4, which is minus 3/4. And now we know what the first column in our matrix map, a corresponding, or matrix is corresponding to that linear map. We now know that A11 bar, A21 bar is equal to minus 3/4 and 9/4, where this is the first column in the matrix representation of T for this new combination of basis vectors. What's the second column of our matrix going to look like? Well, that's going to depend on how the linear map handles the second basis vector in our domain, V sub 2 bar. And that vector was minus 1, 1. This is the basis that we rotated counterclockwise 45 degrees from the standard basis and stretched. This one now is 2 times the first coordinate minus 1/2 times the second. The first coordinate plus 2 times the second. Or we have minus 2 minus 1/2, or minus 5 halves, and minus 2 plus, or I'm sorry, minus 1 plus 2, giving us 1. And that's now supposed to equal A bar, don't want to forget that, the weighting on our first basis vector in the codomain for the second vector in the domain, plus A sub 2 bar W2 bar. Or this is now A12 bar, and our first vector in the codomain basis was 1 minus 1, and the second vector was 1, 1. Which now says that we could write that as W bar A sub, the first entry is 1 or 2, which I've represented as a colon, MATLAB notation, or this is now W bar is 1 minus 1, 1, 1, and our unknown, and that should have been a bar, is A12 bar, A22 bar. And we want that to actually equal what we just computed, which was minus 5 halves and 1. That's again 2 equations and 2 unknowns. We can solve that by inverting that matrix on the left, that 2 by 2 matrix, which says that we now take 1 over the determinant of that matrix, which is the product of the diagonals minus the product of the off diagonals. And we won't learn determinant until the last chapter in the book, but I'm assuming you know how to compute a determinant. And now we exchange the diagonal entries. That was obvious. Since they were equal, you can't tell that we exchanged them. Maybe I should have had them in different colors. And we change the sign of the off diagonals. And that now is going to, let me just find that inverse first, or this is now, if we look at the determinant is 1 minus a minus 1, or 2, and we have 1 minus 1, 1, 1. That's the inverse of that W bar matrix. A1 2 bar, A2 2 bar is going to then be this 1/2, 1 minus 1, 1, 1 times minus 5/2 and 1. Or I now have minus 7/2, which I'm going to scale by 1/2, giving a minus 7/4. And I have minus 3/2 multiplied by 1/2, or minus 3/4. And this now is the second column in the matrix representation of T. So that now this matrix representation of T from V1 bar to V2 bar into W1 bar, W2 bar becomes minus 3/4, 9/4, and minus 7/4, minus 3/4. And this, if I call this as I said I would to begin with, if that's A bar, that as a matrix maybe doesn't look the same as A, does it? But it's supposed to do the same thing. It's supposed to map from P1 to Q1. It's just it's taking a different representation in the domain to another point in a different representation than the first mapping A did. It was working with 2 different basis representations in the domain and the codomain. Can we check that? Suppose now we do a check and we say now we want to go P1V through this, let's say A bar, to generate Q1W bar. Q1W bar is now this minus 3/4, 9/4, and minus 7/4, minus 3/4. That's the A bar times P1V, which was 1, 0. That actually has the effect of simply pulling off the first column in A bar to produce minus 3/4 and 9/4. And what does that mean? That means we take the first basis vector in our codomain, scale it by 3/4, and go in the opposite direction. And then add to that 9/4, or a little bit more than 2 times the second basis vector direction. What I'm saying is we now want to take minus 3/4 times W1 bar plus 9/4 W2 bar. Or that's now minus 3/4, and W1 bar was 1 minus 1. 9/4 times 1, 1. Or that's now minus 3/4 plus 9/4, and 3/4 plus 9/4, or 6/4 and 12/4, or 3/2 and 3. Is that where we wanted to go? If we look at what we had graphically or pictorially, we said that we wanted to end up at a point in space here. Whoops, maybe that's... So I've cut my coordinates down a little bit. We started at a point P1, and we said that we wanted to go in this basis 3/4 in the direction opposite to W1 bar. W1 bar, wasn't it down here? And we wanted to go opposite to that by about 3/4 of the distance. And now we need to add to that 2 1/4 in the direction of W2 bar, but W2 bar was that direction. So we move that direction 1, 2, well, I guess my distance is now the square root of 2, so I needed to go 1.4, 1.4, and 1/4 to put me, and maybe I didn't go up quite right, because I'm supposed to be right there, at 3/2, 3. So maybe I should say that now I needed to go up here about 1, 2, and now I'm missing it by the exact amount on the other side, but you get the idea. This is now 3/4 minus W1 bar, and this vector is 9/4 W2 bar, and here is our Q sub 2. And we moved between P1 and Q2, or Q2, I never defined a Q2, did I? That's supposed to be Q1. And that's the same point that we get to if we start or use the standard basis. We get to 3/2 and 3. And if you sketch it maybe a little more carefully and accurately, you should be able to get in the same location from P1 to Q1 using whatever basis you have, and in particular what we started with, either the standard basis or the barred basis vectors. And the point is that you might have a matrix that you really don't know what that corresponds to unless you know what the bases are that it's mapping from and to. What it represents might be something completely different depending on what your bases are in the domain and the codomain. Or another way of saying that is it's important to keep track of which basis are being used for V and W. Thus, the matrix representation of T, that now I'm going back to my standard usage for V and W, for the domain and the codomain, this linear map, thus the matrix representation of that linear map T on the basis V1, V2, V sub n, and W1, Wm, let's say in general. We've already written that, but let's go ahead and just say that that's going to be represented as this matrix T, comma, V1, Vn, W1, Wm, if our linear map is, let's say, from an n-dimensional vector space to a Michigan dimension vector space, n. Now, when the choice of our basis is obvious, for example, maybe we're using the standard basis, we may not write all of that out. When the choice of our basis for the domain and or the codomain is obvious, then we will use, let's say, the simpler notation the matrix representation of our linear map T. An extremely important note is the following. As with vectors, maps, which we had as matrices A and A bar, maps have an existence separate from their matrix representation. We had an A and an A bar that corresponded to the exact same linear map. So maps have an existence separate from their matrix representation. Choosing different bases changes the values or the scalars in the matrix, but does not change the meaning or the truth or falsity of any statement about the map. Nor does it change any physically relevant numerical result. So what the map is doing is sort of independent of how we are representing it, is maybe another way of rephrasing that. And what we may be more interested in is what is the map really doing. But once we have these matrices, you now know how to add and multiply matrices by matrix addition, scalar multiplication. We also know how to multiply matrices. We know how to multiply a matrix with a vector. Let me just say that you need to be comfortable with matrix addition. That's just element-wise addition of the elements in each matrix. Matrix addition is element-wise. But what has to be true about the matrices that you're adding? They have to have the same dimension. So the matrix addition is element-wise on matrices of the same, let's say, size. Scalar multiplication scales values element-wise. And because these operations are closed, and because we're using the standard arithmetic operations, we get all the other properties too. Meaning now we could actually define a new vector space that's a matrix. The vector space that we can define is now a matrix. It has m rows, n columns, and has entries or elements in the field F, either real or complex. This is now the set of all m by n matrices with elements in F. What's the dimension of this vector space? If you needed to now sort of keep track of what's going on, how many sort of standard vectors would you have to create to find a basis where those are now linearly independent and span this entire space? So now think of a 2 by 3 matrix. So now you need to have basically 6 different 2 by 3 matrix. So if it's 2 by 3, you now have 6 elements that you could basically individually or independently adjust in this set of entities, which are matrices, so that the dimension of that matrix that's m, n, f is now mn. So it takes m times n numbers to specify anything in that new vector space. Wow, we are out of time, really. So I'll figure out what we want to do next, but think about completing chapter 3. How much time I will spend on that next time, I don't know. Maybe we'll move into chapter 4 and 5. 4 we're going to quickly move through, which is polynomials, and then we'll get into 5, which is dealing with operators. Yes? The test will cover the material up through homework number 3, whatever that is. So homework 3 is due on Friday, and so that material, homeworks 1, 2, and 3, will be what we deal with on exam number 1. Okay?